Hi guys, it's Daniel here, and today we're going to do question number 6 of the 2008 IMO. So since it's question 6, it means it's the hardest problem of the IMO, but don't be intimidated, because in fact, I'll show that if we know some theorems from geometry, this is actually quite a motivated problem. So let's get started and do the problem. So we have that ABCD be a complex quadrilateral, etc., etc. I'll just draw the diagram. So let's see. Denote incircles of A, B, C, and ADC, omega 1, omega 2. So here is incircle omega 1. Let's see. There we go. This is omega 1. Suppose there exists a circle omega tangent to ray BA beyond A, ray BC beyond C. Okay. Let's do that as well. This is omega. And let's see, ABCD. We need an A and a C. Here's A, here's C. Tangents. Here's D. And that means this here is omega 2. Okay, so that is our diagram here. Let ABCD be convex quadrilateral with BA not equal to BC. Denote incircles of triangle ABC and ADC by omega 1 and omega 2 respectively, as shown on the diagram. Suppose that exists a circle omega tangent to ray BA beyond A and ray BC beyond C, which is also tangent at lines AD and CD. So AD, CD. They're all tangent at these points. Prove that the external tangent, the common external tangent of of omega 1 and omega 2 intersect on omega. So these intersect as so. Okay. And we need to, so we want to show that these two lines intersect on omega. So before we do anything here, the first thing that we think of when we think of the common external tangents to omega 1 and omega 2 is Monge's theorem. And Monge's theorem states that if we have three circles, then the common external tangents of them pairwise is going to be on a single line like this. And what's more, this is true not only when they're all common external tangents, but when two of them are internal tangents as well. And we'll be using that version of Monge's theorem as well. So we have three circles here, and we have one of the two external tangents already. So actually we have two of them already. We have the two omega 1 and omega 2 having the common external tangents concur at this mystery point. And we also have omega 1 and omega with their common external tangent at B. So we already have two, so this highly suggests that we should probably draw the third one in, which is the common external tangent between omega and omega 2. So, like so. And what does Monge's theorem state? Monge's theorem states that B, our mystery red point, and this purple point are collinear. And if we use the alternate version of Monge's theorem, which has two of them be the internal tangents instead of external tangents, then we can do the exact same thing, because here we have an external tangent between omega 1 and omega 2 as the mystery red point. We also have an internal we have the intersection of the internal tangents between omega 2 and omega at D. So if we draw the internal tangents between omega 1 and omega, then that point, our mystery point, and D are going to be collinear. But I'm not going to draw that right now because it'll make the diagram too cluttered. So this is all nice and well, but how exactly are we going to proceed from here? We could try to, well, the idea is that we could take the line B to this purple point right here, and then take the line D to the other point that is formed from the intersection of internal tangents, and then prove that they concur on the circle. So that's a possible way to prove it, except for the problem is that this purple point right here is not very nice either. It doesn't seem like we can work with it that much. It doesn't seem to relate with anything. So we'll need to dig a little bit deeper. So the second thing that we should probably think about is what exactly is this mystery point, this mystery red point. In all the problems where we have two things concurring on some other random thing, I can guarantee you that this concurrency point is not going to be random. There's going to be some sort of special property with it that relates to the rest of the problem, or else it'd simply be not solvable. So what we probably want to do is seek out what this special point is, what property this special point has that might help us. And if you try to look at this diagram, especially if you draw AC parallel with what you think of as the horizontal, if you draw AC as horizontal, then you might notice that no matter how you draw the diagram, this red point seems to always be on the top of the circle. In other words, if we draw the tangent to omega at this mystery point, then this tangent line seems to always be horizontal, or always parallel to AC. And this is the property that we need in order to move further into this problem, because since this point is on the top of the circle, then we might also be able to use the other points that are on the tops of omega 1 and omega 2 to try to help us. This is further motivated by the fact that omega 1 and omega have their common tangents at B, which means that if you have a homothency, there exists a homothency centered at B that sends omega 1 to omega. And similarly, there exists a homothency centered at D sending omega 2 to omega. So maybe if we could use the top points or the bottom points of omega 1 or omega 2, then we might be able to solve this problem. So, how are we going to use these points? Well, as I said, we can send omega 1 to omega by homothency, which also sends the top point of omega 1 to the top point of omega by the same homothency. And if we had a homothency centered at D, then we could send the bottom point of omega 2 to the top point of omega. So we should probably mark those points. And for now, I'll focus on the top point of omega 1. Now, we also have this purple tangent right here, and we can have a homothency centered at this purple point that sends omega 2 to omega as well. So, in particular, it sends the top point of omega to the top point of omega 2, and the special part about the top point of omega 2 is that it is, in fact, the tangency point of omega 2 in AC, because we drew AC to be horizontal. So if we can prove that omega is the top point, or the red point is the top point of omega, then we also know that the purple point, the top point, the tangency point of omega 2 in AC, and the red point are collinear. And this might be able to give us the break we need, because we want to prove that B, the purple point, and the red point are collinear. So it'd be quite nice if B, the top point of omega 1, the purple point, tangency point of omega 2 in AC, and the red point were all collinear, because that would satisfy all the properties that I've just named right now. So we should probably set out to try to prove this. So how might we go about proving this? Well, the first thing we know is that B, the top point of omega 1, and the top point of omega are already collinear. We already know this because it's just a homothency. We're already given it. So now we just need to prove that we want to prove that the purple point as well as the tangency point of omega 2 and AC also lie on this green line. And because we know that the purple point, the tangency point of omega 2 and AC, and the red point are collinear, this means that in order to prove that both of these lines are on the green line, all we need to do is prove that one of them is on the green line. And since, like I said, the purple point is kind of nasty, we're going to use the tangency point of omega 2 and AC. We're going to prove that this point lies on the green line. So how might we go about proving that? So the nice thing about this point right here is that it's on AC. So if we try to do a homothety sending omega 1 to a circle that's tangent to AC, then it should be tangent to AC at the same point as omega 2 in order for the tangency point of AC and omega 2 to be on the green line. In fact, the tangency point of omega 2 and AC, in other words, should be the x touch point of a triangle ABC, or the BX touch point. In other words, the point at which the BX circle of triangle BAC touches is tangent to AC. So we want to set out to prove that this point right here, which I will call T, is the BX touch point of triangle ABC. So now we just need to use some properties of the X touch point. So there's one more thing that we haven't used yet in this problem, and that's that AD and CD are tangent to omega. So we have the fact that these four lines, AB, BC, CD, and DA, are all tangent to omega. Well, that means that omega is kind of like an X circle to this quadrilateral. And there's this one theorem that we can use that addresses when a quadrilateral has an X circle or incircle, and that theorem is called Pitot. I'm not quite sure how to pronounce this, but it's called Pitot's theorem. And Pitot's theorem states that if a quadrilateral has an incircle, then the sum of these two opposite sides is equal to the sum of these two opposite sides. And if it has an X circle, as we have right now, then the sum of the two, it's going to still be the sum of two sides equals the sum of two sides, but it'll be a different set. It won't be opposite sides anymore. And we can just figure out by ourselves which two sides sum to the other two sides. So let's go ahead and do that right now. So for convenience, let's let this point be E and this point be F. The intersection of A, B, and CD is E, and the intersection of AD and BC is F. So we want to prove that two of the sides of triangle, or not triangles, quadrilateral BEDF sum to the same thing as the sum of the other two sides, because this omega is one of the X circles, I guess you can call, of quadrilateral BEDF. So in fact, it's BE plus DE equals BF plus DF. And to prove this, well, let's move down to a simpler diagram for now. So we have these four tangencies. 1, 2, 3, 4. Okay. And we want to prove that this thing plus this thing equals this thing plus this thing. Okay. So first off, let's mark these different colors. Okay, so the first thing we notice is that because we have these tangencies right here, that this thing, this segment from here to here is equal to this segment from here to here, because they're both tangents from a point to omega. So since the purple, these two lengths are in the purple and the red sides respectively, we can cancel them out. So now, how about the rest of this length? Well, by the same reasoning, the rest of this length right here is equal to this segment right here. And the rest of this length right here is equal to this segment right here, where it goes from E to the tangency point and F to the tangency point. So now what we need to prove left is that this segment from the very top to the tangency point is equal to this segment from the very top to the tangency point, but this again is the same property, that a point to the two tangents from a point to a circle are the same length. So in fact, everything on both sides cancels out, and we have our desired equality. And actually, in a similar fashion, we can show that since omega is an X circle to triangle AECF as well, we can also show that AE plus CE equals CF plus AF. Let's see. Yep, I believe that's true. So by the same way, we can prove this. So now we have two equations that we have not used yet. And they're two length equations, and we want to use them to prove that T is the BX touch point of triangle ABC. So we probably want to use a length property of the BX touch point. So a length property of the tangency point of an X circle with the triangle is that AT, let's write it here, AT should equal CT prime, where I'll let T prime be the tangency point of the incircle with AC. So this is a property of the X touch point, and let's see if we can arrive at this property from these two equations. So if we subtract those two equations from each other, then we get that, conveniently enough, AB minus CD is equal to BC minus DA. So this is true. And now let's take a closer look at how we might move this to AT equals CT prime. So drawing the stuff here. Okay. So we have that AB minus CD is BC minus DA, which means that AB, let me label these. AB plus AD is equal to BC plus CD. So we have that this length plus this length is equal to this length plus this length. So now let's try to cancel out stuff from both sides of the equation again. So we have that these two lengths, these two segments, are the same since they're both tangents. So we can cancel them out, as well as these two. Cancel those out. And now let's see. This segment is equal to this segment. And this segment is equal to this segment right here. Similarly, we have that this segment is equal to this segment right here. And this segment, is equal to this segment. So we have that the sum of, label these, we have the sum of T prime we have the sum of AT prime plus AT is equal to CT prime plus CT after canceling out both sides and moving them all to segment AC. How might this help us? Well, AT prime is equal to AC minus CT prime, and AT is equal to AC minus CT. So we have 2AC minus CT prime minus CT is equal to CT prime plus CT, which means that AC is equal to CT prime plus CT, right? Except for we see that CT prime is equal to CT prime is equal to AT, or no, CT prime is equal to AC minus AT prime. And then rearranging again gives AT prime is equal to CT, which is almost exactly what we want. But AT prime equals CT is equivalent with AT equals CT prime. So we get what we want, and T is indeed the BX touch point of triangle ABC. So let's review what we just did here. First, we know that the green line exists that connects B, the top point of omega 1 and the top point of omega, and we just proved that T also lies on this line. And we also know that the purple point, T, and the red point are collinear, which now we know that the purple point is on this green line. So now we finally know that B, the purple point, and the top point of omega are collinear. So now we can do the exact same thing on the other collinearity we get from Monge's theorem, passing through D, the top point of omega, and the intersection of the tangents omega 1 and intersection of the internal tangents of omega 1 and omega right here. So this point D and the top point of omega are also collinear, right? Except for, here's the thing, we know that through Monge's theorem that the intersection of the external tangents of omega 1 and omega 2 is collinear with B and the green point, and it's also collinear with D and this new point that I drew in right now. But the thing is, they already both intersect at the top point of omega, so that means the intersection of the external tangents of omega 1 and omega 2 must actually just be the top point of omega. Therefore, they actually intersect on omega at the top point. So we are finally done. Hi guys, it's Daniel here. All of you probably have heard of something called Fermat's last theorem, which states that x to the power of n plus y to the power of n plus z to the power of n equals z to the power of n has no positive integral solution